The 737 airplane is powered by two CFM56-7 engines. The engine is an axial flow turbofan with two rotors. The N1 rotor has a fan, a low-pressure compressor section, and a low-pressure turbine section. The N2 rotor has a high-pressure compressor section and a high-pressure turbine section. The N2 shaft turns the accessory gearbox. The accessory gearbox drives the integrated drive generator, the oil pumps, the fuel pumps, and the hydraulic pump. Air passes through the fan. Some of the air goes through the compressor for combustion. A large part of the air goes through the duct to provide most of the thrust. Next is an overview of the engine fuel system. The fuel system supplies fuel from the fuel tanks. The fuel goes through the first stage engine fuel pump. The fuel is heated by the IDG oil cooler and the fuel oil heat exchanger. The fuel then goes through a filter that removes solid contaminants. After a second stage pump and a second filter, the fuel goes to the hydromechanical unit, or HMU. Here the electronic engine control, or EEC, adjusts the fuel flow. Part of the fuel goes to the combustion chamber and the unused fuel returns to the fuel pump. Next is an overview of the engine oil system. The oil pump pressurizes the oil from the tank. The oil goes through an oil filter and continues to the engine bearings and accessory gearbox. The oil temperature and pressure sensors are located here. The scavenge pumps collect the oil from the engine. The oil then goes through an oil scavenge filter to remove contaminants. The oil goes through the fuel oil heat exchanger before it returns to the tank. Each engine has flight deck controls. You manually set power with the thrust levers, or automatically with the auto throttle system. Each engine is controlled by an EEC. The EEC uses the thrust lever position and environmental inputs to control the engine's thrust. The engine indications are shown on the upper and lower display units. Primary and secondary engine indications are shown on the upper and lower display units. If a DU fails, the engine indications automatically move to the other DU in a compact engine display. N1 and EGT are the primary engine indications. Fuel flow is displayed full-time on the upper DU below the primary engine indicators. N2 fuel flow, oil pressure, oil temperature, oil quantity, and engine vibration are the secondary engine indications. They are discussed in a different lesson. There are some differences in the primary engine indications. The pointers show the related digital readouts position on the indicator. The normal range is white. Move the thrust levers forward and look at the N1 indications. The white commanded sector arc outside the dial shows the difference between commanded N1 and actual N1. Move the thrust levers to idle and look at the N1 indications. The reference N1 bug and reference N1 readout are shown with the N1 indications. They are discussed in a different lesson. A red EGT start limit line is shown during engine starts. The start limit line is discussed in a different lesson. Let's look at the fuel indications differences. The type of information that the digital readout and related pointer show still depends on the position of the fuel flow switch on the engine display control panel. In the rate position, the digital readout shows the rate of fuel flow. Momentarily move the fuel flow switch to used. The readout changes to the current fuel used since the last reset. After 10 seconds, the display goes back to fuel flow. Momentarily move the switch to reset. In the reset position, the readout first shows the fuel used, then decreases to 0, and then goes back to fuel flow. We will now look at new indications for non-normal conditions. If an N1, N2, or EGT value goes above an operating limit, the dial, readout, and box change color. In this example, the EGT is more than the maximum continuous limit. The indication becomes amber. If the temperature goes above the maximum operating limit, the indication becomes red. When the temperature decreases below the limit, the indication changes back to white. If an N1, N2, or EGT in-flight exceedance occurs, the box becomes red after engine shutdown on the ground. In this example, the EGT had an in-flight exceedance. An amber engine fail alert is shown if the related engine's N2 decreases below a stabilized idle of approximately 50%, and the engine start lever is in the idle position. The alert is removed if N2 increases above stabilized idle, or the start lever is moved to cutoff, or the engine fire warning switch is pulled. A magenta crossbleed indication shows if a crossbleed start is necessary for an in-flight engine start. The secondary engine indications are oil pressure, oil temperature, oil quantity, and the Airborne vibration monitor system. The oil pressure and oil temperature indications are vertical indicators with moving pointers. The oil pressure indication is shown in PSI. Oil temperature is measured in degrees Celsius. The oil quantity digital readout shows oil quantity in percent of full or in quarts or liters. Low oil quantity is displayed by reverse video and a low message next to the quantity indicator. The normal operating range for oil pressure and temperature is shown in white. The operating limit for both is shown here by a red band. When the oil temperature enters the caution range, the display changes to amber. The size of the oil pressure caution range is a function of the N2 RPM. The amber band increases in size as N2 increases from 65% to its red line. When N2 is below 65%, there is no amber band. The Airborne Vibration Monitoring System, or AVM, monitors engine vibration levels to track rotor imbalance. The indicator displays units of vibration. It shows the higher engine vibration level of N1 or N2. High vibration is displayed by reverse video, indicated by the AVM above 4.0 units. Let's now look at some non-normal indications. The first indication is a low oil pressure condition. Since the output pressure of the oil pump is unregulated and varies with engine speed, engine oil pressure may go into the amber band and the pointer turns amber. If the oil pressure goes into the amber band with takeoff power set, do not take off. Oil pressure in the amber band is not normal at high thrust settings. If the pressure continues to decrease and reaches the red limit, the display end pointer turns red and the low oil pressure alert illuminates. The pressure is now too low for continued engine operation and the engine must be shut down. Next, let's look at a high oil temperature condition. The oil temperature is measured prior to the oil entering the gearbox. If the oil temperature goes into the amber range, the pointer and displays turn amber. With temperature in the amber range, you can operate an engine for 45 minutes before an engine shutdown is required. If the temperature continues to increase and reaches the red line limit, the pointer and display turns red. The oil temperature is now above the operating limit for continued engine operation, and that engine must be shut down. There is one other engine alert associated with the engine oil system, the oil filter bypass. The scavenge filter has a bypass feature with pressure sensors at the inlet and at the outlet. If the filter becomes contaminated, the oil filter bypass alert illuminates to show a bypass of the filter can possibly occur. If the oil filter bypass alert remains illuminated after thrust reduction, that engine must be shut down. When the low oil pressure and oil filter bypass alerts display, they flash for 5 seconds, then stay steady until the related condition no longer exists.
The flashing indication is inhibited during takeoff. When inhibited, the alert immediately illuminates steady. In this example, there is a low oil pressure indication during the takeoff roll.
The thrust mode display, N1 reference readout, N1 reference bug, and N1 maximum bug appear in and around the N1 display. The N1 reference bug and the N1 reference readout both indicate the active N1 limit for the thrust mode currently displayed in the thrust mode display. The active N1 limit is normally calculated by the FMC. The thrust mode display indicates the active N1 limit reference. There are many possible enunciations. The thrust mode display is discussed later in this lesson. An N1 maximum bug is present on the N1 display. During most phases of flight, the N1 maximum bug is an EEC computed value, representing the maximum rated thrust the engine is capable of producing. When a fixed D rate has been selected on the FMC CDU, the N1 maximum bug displays at the N1 value, computed by the FMC, representing the fixed D-rated thrust the flight crew has selected. This N1 value will be used until the D rate is no longer selected. In this example, a D-rated takeoff 1 with an assumed temperature has been selected. The N1 maximum bug will show the N1 for a D-rated takeoff, but it will not reflect the N1 value for an assumed temperature takeoff. However, the N1 reference bug and the N1 reference readout will show the N1 value for the assumed temperature. The N1 reference bug and the N1 reference readout can be controlled by the N1 set selectors on the engine display control panel. The outer knob has 4 positions, both auto, 1 and 2. In the auto position, the FMC automatically sets the N1 reference bug and the N1 reference readout. In the 1, 2, or both position, the N1 reference bug and readout are controlled by the inner knob. The thrust mode display is MAN to indicate manual N1 positioning. In this example, the outer knob is in the 1 position. Only the N1 bug and readout for the number 1 N1 indication will change as the inner knob of the N1 set dial rotates. Now set both reference N1 readouts and bugs to 86.8. First, turn the outer knob to both. Next, turn and hold the inner knob until the readout and related bug read 86.8. Next, let's look at the thrust mode display. The thrust mode display is calculated by the FMC. The thrust mode display is the active N1 limit reference mode for autothrottle and manual thrust control. If the FMC calculations become invalid, the autothrottle computer calculates a degraded N1 limit for the affected engine or engines, and the autothrottle limit indication illuminates. These are the thrust mode displays available for the different phases of flight. Touch each mode to see its definition. Each engine is monitored and controlled by an electronic engine control, or EEC. The EEC uses thrust lever position and flight conditions to control forward thrust, reverse thrust, and idle. The EEC supplies N1 and N2 redline protection. If N1 or N2 goes near the red line, the EEC commands a decrease in fuel flow. However, you must monitor the EGT limit because the EEC does not supply EGT redline protection. The controls for the EECs are on the aft overhead panel. Both EEC switches are guarded and should be in the on position for pre-flight and during normal operations. The EECs have two modes of operation, normal and alternate. Let's first look at the normal mode. When the EEC switch is in the normal position, the white on light is in view. In the normal mode, the EEC calculates a commanded N1 value based on the thrust lever position and flight conditions. The EEC compares commanded N1 to actual N1 and adjusts fuel flow to change engine speed until actual N1 equals commanded N1. The EEC can operate in one of two alternate modes, soft or hard. If the necessary normal mode inputs are not available to the EEC changes to the soft alternate mode automatically. In this example, an input to the number 1 engine EEC is gone. The alternate light, the engine system annunciator, and master caution lights illuminate. This mode is the soft alternate mode because the EEC switch stays in the on position and the alternate light has illuminated. The EEC now uses the thrust lever position and locks in the current ambient conditions to calculate maximum N1 data. The EEC then internally locks in this calculated maximum N1 to prevent uncommanded thrust changes. The hard alternate mode is entered if the thrust lever is moved to idle or if alternate is set with the EEC switch. The hard alternate mode is also set with the EEC switches. You can manually set the alternate mode when you are in the normal mode or the soft alternate mode. To control thrust in the hard alternate mode, the EEC uses thrust lever position with internal data. The hard alternate mode removes the parameters that were locked in when the EEC went from normal mode to soft alternate mode. When the alternate modes are removed, thrust lever movement can occur. Before you set the hard alternate mode, move the thrust levers to mid position, and if the auto throttle is engaged, disengage it. This prevents the engines from exceeding the thrust limits and allows the thrust levers to remain manually positioned. Set the alternate mode for engine number 1. First, lift the engine number 1 EEC switch guard. Next, push the EEC switch. The on light goes out of view and the alternate light stays illuminated. The EEC is in the hard alternate mode. If one EEC is in the alternate mode, it is necessary to put the other EEC in the alternate mode. This makes sure the two engines operate in the same mode and there is no thrust lever stagger. Next, we will discuss engine idle. 3 different idle modes are available to the EEC. They are ground minimum, flight minimum, and approach. The EEC selects ground minimum idle for ground operations. Flight minimum idle for most phases of flight. And approach idle in flight if flaps are in landing configuration. Or engine anti-ice is selected for either engine. Approach idle improves engine acceleration time for go-around. Approach idle is maintained for 5 seconds after touchdown, then ground minimum idle is selected. Finally, we'll discuss the engine control lights. The engine control light illuminates if faults are detected by the EEC that require maintenance. The light operates only when the airplane is on the ground. The master caution and engine system annunciator lights also illuminate. Reset the master caution system. If either engine control lights illuminate, the airplane cannot be dispatched. This is a review of the primary and secondary engine indications. Touch each indication to display information. When finished, touch the arrow. Each engine is equipped with a thrust reverser system for normal landing and rejected takeoff operations. Each thrust reverser consists of a left and right translating sleeve. Aft movement of the translating sleeves cause blocker doors to deflect air forward through fixed cascade guide vanes. This causes reverse thrust. For normal operation, engine number 1 thrust reverser uses hydraulic system A pressure, and engine number 2 thrust reverser uses hydraulic system B pressure. If there is a failure of hydraulic system A or B, the standby hydraulic system is the emergency source of pressure for the 2 thrust reverser systems. In this example, Hydraulic System A failed. To use the thrust reversers, the airplane must be on the ground with the forward thrust levers at idle. The reverse thrust levers are on the control stand. Each reverse thrust lever has 5 positions: stowed, interlock stop, and 3 positions of reverse: detent 1, detent 2, and maximum reverse. There are 2 thrust reverser system indicators: the reverser light on the engine panel and the reverser indication above the N1 indications. During pre-flight and normal in-flight operations, the reverse thrust levers are in the full down or stowed position. In this position, the translating sleeves are stowed and locked. A mechanical interlock in the thrust lever assembly prevents movement of the forward and reverse thrust levers at the same time. The forward thrust levers must be in the idle position before the reverse thrust levers can be moved. Raise the reverse thrust levers to the interlock stop position to see how the engine number 1 thrust reverser system operates. The initial motion of the reverse thrust levers releases the electromechanical lock and unlocks the translating sleeves. Next, the isolation valve opens if the air-ground sensor is in the ground mode, or a radio altimeter shows altitude of less than 10 feet. With the isolation valve open, the control valve moves to the deploy position. And hydraulic pressure starts to move the translating sleeves to the deployed position. An amber reverser indication illuminates above the engine N1 indication. It shows the translating sleeves are in transit. An interlock mechanism restricts further movement of the reverse thrust levers until the sleeves are near the deployed position. As the sleeves reach the deployed position, the reverse thrust levers can be raised to detent number 2. When the sleeves are deployed, the amber reverser indication changes to green. Raise the reverse thrust levers to detent number 2. In detent number 2, the EEC sets sufficient reverse thrust for normal operation. If maximum reverse is necessary, you can raise the reverse thrust levers beyond detent number 2. Now raise the reverse thrust levers to the maximum reverse position. The EEC now sets maximum reverse thrust. When reverse thrust is no longer necessary, lower the reverse thrust levers to detent number 1. In detent number 1, the EEC now sets a minimum idle. Now lower the reverse thrust levers to the stowed position. The control valve moves to the stow position, and hydraulic pressure moves the sleeves to the stowed position. The green reverser indication changes to amber and shows the sleeves are in transit. After the sleeves are stowed, the isolation valve closes, the electromechanical lock engages, and the reverser indication extinguishes. Look at some non-normal thrust reverser conditions. The thrust reverser system has an auto restow feature. The auto restow system compares the actual translating sleeve position and the commanded reverse lever position. In the event of an incomplete stow, or if a translating sleeve is sensed out of the stow position, the auto restow system opens the isolation valve and directs hydraulic pressure to stow the reverser. If the auto restow system is activated, the isolation valve remains open and the control valve is held in the stow position until corrective maintenance action is taken. Or the thrust reverser is deployed normally. If the isolation valve or the selector valve is not in the commanded position, the reverser light on the aft overhead panel illuminates. In this example, the reverse thrust levers are stowed, but the number 1 engine isolation valve is open. The reverser light also illuminates if the auto restow circuit is activated, or if the positions of the left and right translating sleeves on each engine do not agree. Since the light can illuminate during normal operation of the reverser, there is a time delay before the master caution and engine system annunciation lights illuminate. Reset the master caution system. With the reverser light illuminated, flight crews should be aware that additional system failures can cause in-flight deployment of the reversers. However, you can expect normal reverser operation after landing. If the reverser indication illuminates in flight, the indication is incorrect, or a translating sleeve is mechanically unlocked. If a translating sleeve has mechanically unlocked, the forward thrust lever may be restricted and the unstowed sleeve can produce some yaw or buffet. The affected engine must be shut down. If the forward thrust lever is not restricted and no buffet or yaw exists, the reverser indication is incorrect, and the affected engine can be operated normally. Bleed air and electrical power are required for engine starts. Bleed air turns the starter motor. The sources of bleed air for engine starts are the APU, a ground air cart, or the other engine. Today we will use the APU to supply the starter air. Electrical power opens and closes the engine start valve. Each engine has two igniters. The AC transfer bus supplies power to the left igniter, and the AC standby bus supplies power to the right igniter. The engine start lever has two positions. The cutoff position de-energizes the ignition system and closes the engine fuel shutoff valve and the spar fuel shutoff valve. The idle position energizes the ignition system through the EEC. Electrically opens the spar fuel shutoff valve and electrically opens the engine fuel shutoff valve through the EEC. Controls for the engine start and ignition system are on the engine start panel. The ignition select switch has three positions. Ignition left and ignition right select the related igniters for the two engines. The both position selects the left and right igniters for each engine. Each engine start switch has four positions. When the engine start switch is moved to the ground position, the start valve opens, and the engine bleed air valve is given a signal to stay closed. The start valve open alert illuminates on the engine display to show the start valve is open. For ground starts, the EEC arms the selected igniter. For in-flight starts, the EEC arms the left and right igniters. In the continuous position, the EEC arms the selected igniter. In the flight position, the EEC arms the left and right igniters. The continuous and flight positions have no effect on the position of the start valve or the engine bleed valve. This is a review of the engine start and ignition system. Touch each control to show information. When finished, touch the arrow. Let's now start the engines. The captain announces the engine start sequence. Normal start sequence is engine number 2, then 1. It is recommended to change the selected igniter for each flight. For today, select the right igniter. Move the number 2 engine start switch to ground. The start valve opens, and the start valve open alert shows on the engine display. As the starter motor turns N2, the N2 indication starts to increase. Before you move the start lever to idle, make sure there is movement in the N1 indicator. And N2 is at 25%. Or at maximum motoring and a minimum of 20% N2. Maximum motoring is when N2 acceleration is less than 1% in approximately 5 seconds. Now move the right start lever to idle. The fuel flow indication starts to increase. Within 10 seconds after the start lever is moved to idle, the EGT indication shows an increase in temperature. At 56% N2, the engine start switch moves to off. The start valve closes, the engine bleed air valve opens, and the start valve open alert extinguishes. The first officer makes sure the alert is extinguished and the engine start switch is off. The first officer tells the captain when the starter has cut out. If the engine start switch does not move to off automatically, the first officer moves the switch to off. An increase in oil pressure must occur before the indications are stabilized at idle. The first officer tells the captain when oil pressure increases. You must monitor N1, EGT, N2, and fuel flow indications until they stabilize at idle. When the engine indications are stabilized at idle, the other engine can be started. Let's start engine number 1. Move the number 1 engine start switch to ground and monitor engine number 1 indications. When N2 is at 25% and N1 has movement, move the left start lever to idle. Monitor the start until engine number 1 indications are stabilized. Remember, the first officer informs the captain when the starter has cut out and oil pressure has increased. The flight is now completed and the airplane is at the gate. Let's shut down the engines. Before engine shutdown, make sure the electrical buses are powered by the APU or by external ground power. For today, use the APU. Now move the engine start levers to cutoff. This completes the engine shutdown. The EEC supplies engine ground start and flameout protection. For engine starts on the ground, the EEC monitors engine parameters. In flight, the EEC prevents engine flameouts. Let's first discuss protection for ground starts. The EEC monitors engine parameters for hot starts, EGT start limit exceedances, and wet starts. An EGT start limit line shows when N2 is below 50%. A hot start is when the EGT quickly increases, or when the EGT approaches the EGT start limit line. If the EEC gets inputs of a hot start, the white box around the EGT digital readout flashes. The box goes to normal when the engine reaches idle N2, or when the start lever is moved to cutoff. Move the start lever to cutoff. If the EGT is more than the start limit line, the EGT dial, readout, and box color change to red. The EEC shuts off the fuel and de-energizes the igniters. The indication goes to white when the EGT goes below the start limit. After engine shutdown, the EGT box becomes red to show an exceedance has occurred. A wet start occurs when the EGT does not increase after the start lever is moved to idle. Fuel can collect in the engine and on the ground around the airplane. If a wet start occurs and the engine start is not aborted, the EEC shuts off the fuel and ignition 15 seconds after the start lever moved to idle. This is a review of the engine ground start protection. The EEC monitors engine parameters that show a flameout can occur while the engine start switches are on off. The EEC energizes the left and right igniters if there is a sudden N2 decrease, or N2 is below 57%. The EEC de-energizes the igniters after 30 seconds, or when N2 decreases below 50%. Three other types of engine starts: ground air, crossbleed, and in-flight. The first type of engine start uses a ground air source to start the engine. The ground air source is connected on the right side of the airplane. AC power from the APU or ground power must be available. In this example, a ground power cart is used. For safety reasons, engine number 1 must be started first because ground personnel and equipment are in the area of engine number 2. The APU bleed air switch must be off. This closes the APU bleed air valve and isolates the APU from the high start air pressure. Make sure the duct pressure from the ground air source is a minimum 30 psi. Use normal start procedures to start engine number 1. After engine number 1 is stabilized at idle, disconnect the external power equipment. Crossbleed air is used to start engine number 2. Let's now look at a crossbleed engine start. A crossbleed start uses bleed air from the other engine. For today, we'll use engine number 1 to start engine number 2. Make sure the engine bleed air switches are on, the APU bleed air switch is off, and the isolation valve switch is in auto. This makes sure bleed air from engine number 1 is available to start engine number 2, and the APU is isolated from the high start pressure. To start engine number 2, engine number 1's thrust must be increased until there is a minimum duct pressure of 30 psi. Before engine number 1's thrust is increased, for safety reasons, make sure there is no equipment or personnel behind the airplane. Now increase the thrust on engine number 1 until the duct pressure shows 30 psi. Engine number 2 is ready to start. Normal start procedures are used to start engine number 2. After starter cutout, decrease the thrust on engine number 1. Now let's look at in-flight engine starts. There are two procedures used for an in-flight engine start: crossbleed and windmill. The airplane's altitude and airspeed must be checked to find the correct procedure to use. The ground start protections are not available for in-flight starts. The crossbleed start indication is shown if an in-flight crossbleed engine start is necessary. The engine start switch is put in the ground position. For a windmill engine start, there is no crossbleed start indication, and the engine start switch is put in the flight position. Now let's look at some non-normal conditions related to engine starts. There are 5 conditions when you must abort an engine start. The first condition, no N1 rotation, occurs before the start lever is moved to idle. When this condition occurs, the engine start switch is moved to off. 3 abort conditions occur after the start lever is moved to idle.
If there is no increase in EGT 15 seconds after the start lever is moved to idle, or if there is little or no increase in N1 or N2 after the EGT starts to increase, or the EGT quickly approaches or goes above the start limit line, the start must be aborted.
The start lever is moved to cutoff. Motor the engine for 60 seconds in the ground position to discard the fuel and cool the engine. The engine start switch is then moved to off. The last abort condition is no oil pressure by stabilized engine idle indications. The start lever is moved to cutoff. When N2 is below 20%, move the engine start switch to ground. This prevents damage to the starter. After ground is selected, motor the engine for 60 seconds, and then move the engine start switch to off. This is a review of the abort conditions for an engine start. The last non-normal condition related to an engine start is when the start valve open alert remains illuminated after starter cutout. To prevent damage to the starter, all bleed air sources to the starter must be isolated. If the APU or engine bleed air is used for start, the isolation valve and related bleed air valves must be closed. In this example, the APU is used to start engine number 1. Now set the bleed air panel to isolate the related bleed air sources. With the isolation valve switch in close and the engine number 1 bleed air switch and the APU bleed air switch in off, all related bleed air sources are isolated. For all ground starts, move the start lever to cutoff. If ground air is used for engine start, the ground air source must be disconnected. Configure the electric control panel and shut down the engines. Connect the APU. Set the bleed air panel for a crossbleed engine start. After you set the panel, advance the engine number 1 thrust lever to increase duct pressure to 30 psi. The 737 has an auxiliary power unit, which is a self-contained gas turbine engine in the tail cone. It operates the APU generator and is a source of bleed air that can be used for engine start and the two air conditioning packs. The APU inlet is on the right side of the tail cone. The exhaust is through the tail. An electronic control unit controls and monitors the APU operation. The APU automatically stops for a dangerous condition. The APU automatically controls the duct pressure for the engine start and air conditioning. The APU can be started and operated up to the airplane's maximum altitude. The APU can supply electrical power to the two transfer buses. The APU can only supply bleed air up to 17,000 feet. Both electrical power and bleed air are available up to 10,000 feet. To start the APU, use either the 115-volt AC or the 28-volt DC power. The APU start switch, the APU exhaust temperature gauge, the APU status lights, and the APU generator off-bus light is on the forward overhead panel. Let us start the APU with the battery. The battery switch must be on for the APU to operate. It supplies power to the fire detection and APU start circuits. Turn on the battery switch. Move the APU switch to start, pause momentarily, and then release the switch to on. The APU inlet door opens. The APU fuel shutoff valve opens and fuel from main tank number 1 flows to the APU. The battery discharge light illuminates for a short time. The APU low oil pressure light illuminates until the pressure is within limits, then extinguishes. The APU generator off-bus light illuminates when the APU completes the start cycle. The APU generator can now accept a load. The APU is normally turned off before taxi, but it can stay on if you will use it during takeoff. Turn off the APU. When the APU switch is moved to the off position, the APU generator is disconnected and the APU bleed valve closes. This starts a 60-second cooling period. When the cooling period is complete, the APU fuel valve closes. Last, the APU inlet door closes. This completes the APU shutdown sequence. If the APU must be shut down immediately, use the APU fire switch on the flight deck, or the APU fire control handle in the main wheel well, or turn off the battery switch. These are the APU status and caution lights. The maintenance light illuminates when there is a maintenance problem. The APU can be operated. The light is disarmed when the APU switch is off. The low oil pressure light illuminates during start until pressure is within limits. If it illuminates at other times, the APU stops automatically. If a fault is sensed, the APU automatically stops and the fault light is illuminated. The fault light also stays on if the APU fuel valve does not close after shutdown. The overspeed light shows an overspeed or loss of overspeed protection. This also causes an automatic shutdown. The APU generator off bus light shows that the APU is prepared for a load. In flight, the galley buses are automatically disconnected when the APU generator is the only source of electrical power. On the ground, the APU tries to energize all systems unless the load is too large. The electrical load for the galleys is removed first. If the load is still too great, the electrical power for the main buses is removed, one bus at a time, until the load is satisfactory. Secure the APU. Wait 20 seconds after the APU generator off bus light extinguishes to let the APU inlet door close before you turn off the battery. Turn off the battery switch.